In this tutorial, we will demonstrate how Tina makes it easy to run, develop, and edit digital circuits written in VHDL, and finally download them to an FPGA chip. This circuit contains two VHDL components. On the left is a prescaler or divider circuit, which currently has a division factor of 2. We will demonstrate the role of the prescaler later in the tutorial. The second component is a binary counter, which counts the pulses after the prescaler. First, let's look at the code for the counter by double-clicking on the component. And then pressing the Enter macro button. We see that the counting process is written in 2 lines of code. A conditional statement and a simple incremental statement. The fact that we can view and modify this code dynamically is the beauty of VHDL, and a great advantage of working in Tina. Later, we will see another example of this. First, let's examine circuit operation in Tina's interactive mode. Press the VHDL button. We see that first QA is high, then QB is high, next both QA and QB are high, and so on. The circuit operates as a binary counter. Once all of the outputs are high at the same time, that is, when the output reaches 15, the process restarts. We can also test the circuit on a timing diagram. To do this, select Digital VHDL Simulation from the Analysis menu. Press OK, and the timing diagram of the circuit will appear. Now move the cursor over the signals. We see that counting begins after the clear signal becomes high, and also that once all outputs are high, the counter is recycled to its original 0 state. Let's close the cursor and the diagram menu and see how easy it is to modify or develop the VHDL code. Double-click on the counter, press Enter Macro, and observe the incremental statement. In VHDL, the entire counting process can be completed with a simple incremental statement. Let's edit this statement and change the increment from 1 to 2. This means that with each clock pulse, the result will be increased by 2. Close the window to see the results of this change. Let's check the result in Tina's interactive mode. As the increment is 2, QA should remain 0 at all times. Press the VHDL button and observe the result. As we can see, first QB, then QC are high, next both are high, and so on. To see this on a timing diagram, release the VHDL button, select Digital VHDL Simulation from the Analysis menu, and press the OK button on the digital VHDL simulation dialog. As we expect, QA remains at 0, and the waveforms on QA, QB, and QC, known from the previous example, are shifted by 1 bit and appear on QB, QC, and QD. Next, we will see how to test this circuit by downloading it to Tina's FPGA development kit. To do this, we need to extend the circuit with FPGA pin connection components, which are found under the Special Components tab. Let's load this circuit from the FPGA folder. Here we see the circuit with the FPGA pin connectors. Certain elements, such as the clock, push button, and LEDs, are pre-connected to the FPGA chip's pins on the development board. The FPGA pin connectors on the schematic diagram ensure that the program we download to the chip will use the same pins. Thus, we can test the code that we download to the chip. To do this, we will use the clock, a push button, and the 4 LEDs on the development board. Before we generate the files needed for the download, let's discuss the role of the prescaler. As mentioned previously, during the simulation, the prescaler operated as a frequency divider by 2. The clock on the development board, however, operates at a frequency of 50 MHz, which is too fast to produce a visible signal on the LEDs. If we want to display the signal on the LEDs, the clock signal must be slowed down. We can modify the code in the prescaler to slow the clock speed. Double-click on the prescaler and click Enter Macro. Here we see the conditional statement, with which we can change the clock speed. If we replace the 0 with 50 million, after 50 million cycles, the prescaler will generate just 1 clock pulse. Thus, the process will operate at a frequency of 1 Hz. Now we can easily observe the activity on the LEDs. Naturally, this cannot be done during a simulation, as the simulation speed is not high enough. We will, however, be able to observe the activity on the FPGA board. Finally, let's create the files needed to upload the circuit to an FPGA chip. To do so, go to the Test and Measurement T&M menu and select Create VHD and UCF file. Here, VHD stands for VHDL code, and UCF is the user constraint file of the Xilinx Spartan chip on the board, which contains the FPGA pin connector associations we previously discussed. We select this command, and the Save As dialog appears. First, we save the VHDL file, then the corresponding UCF file. Now the files have been generated, but they cannot be uploaded directly to a chip. We must use a synthesizer program to do this. In this case, we will use the Xilinx Webpack available for free on the internet. We will demonstrate how to generate the bit files, which can be downloaded to the chip in another tutorial. Now let's download our original circuit to one of the Spartan chips listed on Tina's FPGA development board. Go to the Test and Measurement T&M menu and select Download to FPGA card. Next, go to the Webpack folder in the Examples folder and select the chip. In this case, we select the Spartan 25100. Finally, double-click on the FPGA counter bit file. Now the configuration file has been downloaded to the chip. We see the development board at the bottom right corner of the screen, as well as the 4 LEDs connected to the 4 outputs of the binary counter. The LEDs light up in the same way as we have demonstrated in the simulation. This concludes our tutorial on creating, editing, and downloading digital VHDL designs onto FPGA chips in TINA.